Hello, my dear students. In the previous class, we had discussed about the definition of rings, special type of rings, few examples on rings. Today, I'll take the properties of rings, four properties, very interesting properties. To prove the properties of rings, we have to recall the definition of ring. That means the closure law, associative law, existence of identity, inverse, distributive law, okay, then semi-group under multiplication and so on. First property is like this: a dot 0 is equal to 0 dot a equal to 0, the first property. Second property, a dot of minus b is equal to minus of ab is equal to minus a dot b. Third property, minus a dot minus b is equal to ab. Fourth property, a dot of b minus c is equal to ab minus ac. Let me take the first property. Let me consider a dot 0. I'll rewrite this one as a as it is, binary operation, multiplication. That means dot as it is. I'll write 0 as 0 plus 0. Using left distributive law, we write this one as a dot 0 plus a dot 0. Again, I'll write a dot 0 as 0 plus a dot 0. Right hand side as it is, no change. Since R is a ring, that means the cancellation law holds good. We have two cancellation laws, right cancellation law and left cancellation law. Here I will make use of the right cancellation law. Using the cancellation law, right cancellation law, we can write this one as 0 equal to a dot 0, because a dot 0 get cancelled by using cancellation law. Don't cancel like arithmetic. We have to use only the cancellation laws. Similarly, 0 dot a equal to 0 for all a belongs to ring R. Now we'll take the second property. We know that minus b plus b equal to 0 or b plus of minus b equal to 0. I'll write 0 as b plus of minus b. Let me consider a dot of b plus of minus b. In place of a dot 0, in place of 0, I'll write b plus of minus b equal to what? I'll write a dot 0 in this form. Using distributive law, a dot b plus a dot of minus b equal to 0, because we know the property, first property, a dot 0 equal to 0. Again, the product of these two elements, that is this plus this equal to 0, definitely one will be the additive inverse of the first one. Therefore, a dot of minus b is equal to minus of ab. Similarly, we can prove minus a dot b equal to minus of ab. That means all are equal. Now, third property. Let us consider the product of two elements. First element is minus a, second element is minus b. Product of these two elements can be written as minus of minus ab, because what the second property says, a dot of minus b can be written as minus of ab. That means a dot of minus b. Here minus is inside. Now we write minus in the beginning. Using this property, we write it as minus of minus AB. If I put this mathematical representation in words, we write it as inverse of inverse of inverse of the element what? AB. I mean the product of elements AB. What we get? Minus into minus is plus. Inverse of inverse is what? The element itself, that is AB. Now we'll take the fourth property. A dot of B minus C, we have to prove it as AB minus AC. We can't multiply this one directly because this is not arithmetic or simply algebra. This is order algebra. That means we have to use only binary operation. Since we know that minus is not a binary operation, we have to rewrite this expression in the form what? Plus of minus. Again using distributive law, that is left distributive law. AB plus of AB plus A dot of minus C. Again A dot of minus C can be written as minus AC. This can be written as AB minus AC. So this is the fourth property. Now I'll take one important theorem. Every field is an integral domain. We know the definition of field as well as the definition of integral domain. The common point between these two definitions is what? A commutative ring with unity. Okay. Since F is a field, clearly it is a commutative ring with unity. And every non-zero element of F has multiplicative inverse element. To prove, in order to show F is an integral domain, it is sufficient to show, or it is necessary to show, F is without zero divisors. To prove this part, let me take two elements of F, that means field. Let A and B belongs to F with one condition, A not equal to 0, or you may take B not equal to 0. Out of two elements, one is not equal to 0, such that the product of these two elements equal to 0. Since A is not equal to 0, that means its inverse element exists in F, because F is a field, that means it is a ring. If it is a ring, inverse element exists. Let me consider the product of these two elements equal to 0. Since A inverse is an element of, since A inverse is an element of R, that means F, I will multiply both sides by inverse. A inverse, that is left inverse. I will make use of the left multiplicative inverse here. A inverse dot A, here I will make use of the associative law. A inverse dot 0 equal to 0. A inverse dot A means 1. 1 dot B equal to 0. Again B equal to 0 because 1 is not equal to 0. Similarly, if AB equal to 0 with B not equal to 0, what it gives? It gives A equal to 0. What it shows? It is without zero divisor. By seeing all these results, we can conclude that F is an integral domain. Now I will take an example which is integral domain as well as a field. Here I will take one example. R is a set containing three elements 0, 1, 2. The condition is what? Addition mod 3 and multiplication mod 3. And this set is a ring. That means we have to show it is a commutative ring with unity, and every non-zero element has a multiplicative inverse to say it is a field, and without zero divisors to say it is an integral domain. A dot 2, that means 1 dot 2 under multiplication mod 3 is same as writing 2 dot 1 under multiplication mod 3 is equal to 2. Product of these two elements, 1 dot 2 under multiplication mod 3 is 2, or 2 dot 2 or 2 cross 3, that means under multiplication mod 3 is also 1. That means in both the cases it is not equal to 0. 2 is not equal to 0, 1 not equal to 0. What it shows? It shows that R is without zero divisors. And we know that the multiplicative inverse of 1 is 1 because 1 dot 1 equal to 1. And the multiplicative inverse of 2 is also 2 because 2 into 2 under multiplication mod 3 is 1. Therefore, this example is an integral domain as well as field. Now, one more theorem. A finite integral domain is a field. Here, every field is an integral domain. Now, a finite integral domain is a field. Let me take a finite integral domain consisting n distinct elements. That means all the elements are distinct. A1 is not equal to A2, A2 is not equal to A3, and so on. An minus 1 is not equal to An. Let me take n elements. If X is a member of a finite integral domain D with this condition, X not equal to 0, to verify the definition of field, we need product of two elements. I'll take the product of two elements like this. X dot AI. I may take 1, or I may take 2, or I may take 3, or n. We know that X is a member of D with this condition. I mean X not equal to 0. Since it is a finite integral domain, that means it is an integral domain. I mean it is a ring. Since it is a ring, cancellation law always holds good. Let me prove this theorem by contradiction method. Suppose X dot AI is equal to X dot AJ. Taking this element to the left hand side, we write like this. Again, taking X common, X dot of A minus AJ equal to 0. That indicates AI minus AJ equal to 0 because X is not equal to 0. What it indicates? Here, if X is not equal to 0, AI equal to AJ, which is contradiction because we have chosen all the elements are distinct. Hence, the product of all the elements, it may be XA1, XA2 or XAN, all elements are what? Distinct. What it indicates, it follows that by seeing all these results, we conclude that one of the element of D dash must be unity. Hence, what it shows, every non-zero element of D has its inverse. Whenever we see this statement, that indicates it is a field. This completes the proof of the theorem. In my next class, I'll take few more examples in theorems. Thank you.